Okay, it's 2 p.m. so yes, we can begin. Hi everyone. Thank you guys for coming to today's today's Zoom session. I'm Isabella Kwan. And your other instructor is going to be Andy Jiang. We're going to be today's class is going to focus on algebra and geometry. So just before anything, I'm going to go over a couple of rules. So first of all, I'm about to share my screen, so just let me know if you have any issues with like viewing it. So just some rules. You'll be muted during this whole thing, so ask questions using the Q&A feature. Don't use the chat. For that matter, don't spam the chat. Stop spamming bruh or whatever it is that you've been spamming. It's annoying. Also, try not to use the raise hand feature too much unless you actually have a question. And disruption will result in a kick, so try not to. I'd like to avoid that. But yeah, those are just the rules that you have to follow, so just abide by those. So today's algebra lesson is going to be talking about Vieta's. So Vieta's formula specifically. So I don't know about you, but like the first thing I think of when I think of algebra is like solving for variables. So like solving for x, y, a, b, c, pick a letter of your choice. Before that, let's just do a quick warm-up. This is from this year's AMC8. So I'll give you guys a few moments to think about this one. Oh yeah, don't say your answer in the Q&A section. I actually can't see that at the moment, but okay, let's go ahead and discuss. That's about time. So a good first step is something that you've probably learned from algebra. Isolate the variable. And then how to do that is we should probably take the square root of both sides. By the way, this question has like nothing to do with Vieta's. It's just a quick algebra question as a warm-up. So let's go ahead and take the square root. But this is where it could be a little bit tricky because your instinct would be to let x squared minus 5 be 4, but there's also x squared minus 5 is equal to negative 4. There's both a positive and negative root, a positive and negative like solution. Since you have to be careful when taking the square root because there's either a positive or a negative result. So with that in mind, we can go ahead and solve. to get x is equal to plus or minus 3 on the left side. And on the right side, you have x squared is equal to 1, and then x is equal to plus or minus 1. So all in all, there are 4 different real number x's. Any questions about that? No? Okay. Well, if there's any questions, then Andy can take care of that. So onwards to quadratics. I hope that most of you know what a quadratic is, but just to refresh if you don't. A quadratic is an equation of the form ax squared plus bx plus c for some, in this case, real numbers a, b, and c. Generally, when a question asks to find the root of this of a quadratic, they'll ask for a solution, the solutions of x that satisfy this, where the quadratic is equal to 0. Roots can also be referred to as zeros, and when you want to find roots, there are a couple of ways you can approach this. You can either factor it somehow in the form of like a x minus r1, x minus r2 to get that, or if it's not very if it's not like really easily factorizable, you can also use the quadratic formula. And here's just that as a quick refresher. So there's a quadratic formula. And yeah, that's your general go-to when you want to find the roots of a quadratic equation, but sometimes that's not really easily done because sometimes you won't know all of these coefficients, or sometimes you just want some information about the roots without directly having to solve them, or sometimes it's just a kind of a pain to like find the root and then like manipulate it somehow in a way that we could get like certain pieces of information, and that's where Vieta's formulas comes in. So to explain Vieta's formulas, let's go back to our original form of ax squared plus bx plus c is equal to 0. And we're going to call the two roots of this r1 and r2, r for root. Vieta's formula states that the sum of these two is negative b over a. And the product of these two is c over a. Now keep in mind this negative. That's pretty easily forgettable. Just don't keep that in mind. And yeah, those are Vieta's formulas. So why is that the case? Like, seems like I pulled it out of thin air. Well, what we can do is go back to like the factorized form of this. So we know that ax squared plus bx plus c is equal to x minus r1. Oh yeah, you put an a in front to match the coefficient, my bad. We know that we can factor it like this because we have these two as roots, and that would satisfy this side being 0. Now, when we go ahead and expand the right side using FOIL, we have a times x squared minus r1 plus r2x plus r1 r2. And multiplying that out with the distributive property, we get this. All right, so and now we want to match up all of these coefficients with the ones on the left. So these two obviously line up already. Now we know that these two must be the same. So we have b is equal to negative a times r1 plus r2, and then r1 plus r2 would be negative b over a. Whereas on this side, we take the constant term. We have a r1 r2 is equal to c. So r1 r2 is equal to c over a. Nice. So that's our proof for the quadratic form of Vieta's formulas, and we'll see later on how Vieta's can be applicable to even higher polynomials. But first, let's go ahead and utilize this to solve a couple of questions. So first one, let d and e denote the solutions of 2x squared plus 3x minus 5 is equal to 0. What's the value of d minus 1 times e minus 1? There are a couple ways to do this, so you can go ham. But if you want to find it with Vietas, that's probably a good idea, so you can practice. I'll give you guys a couple minutes on that. Okay, let's go ahead and discuss this one. So, you can probably notice that this equation is you can actually factor it. So if you try it out, you actually get this this works. So then you have x is equal to -5/2 or 1, and then you can put it back in here, and then to get 0, because one of them is 0. Or you could do the quadratic formula, but that's a lot messier. But here we're talking about yes. So let's first list out what we know, because we have D and E are the solutions, roots, blah, blah, blah. D plus E, according to Vietas, is equal to -3/2. And D times E, according to Vietas, is -5/2. So we can take this and expand it. DE minus D minus E plus 1, DE minus D plus E plus 1, and then you can go ahead and substitute these in. So you have -5/2 plus 3/2 plus 1, which is equal to 0, gets us the same answer as before. And yeah, I won't argue for which solution's the better one. In fact, I would probably go for the factoring one, but I just wanted to show how Vietas could be used in this equation. So any questions? Hopefully not. If you have any, then just drop them in Q&A, and we'll move on to the next one then. So this one's a little trickier. Guys, like 3 minutes. let's go ahead and talk about this one. So, like a straightforward application of Vietas just gets you a plus b is equal to m, which doesn't help because we never ask, because they never ask for m and we never know what m is. But before we start problem spamming too much, let's think about what this is asking for. So the question is asking for what is q, and by Vieta's formulas, you know that the q is equal to the product of the roots, since this coefficient is actually just 1. So we know that a plus 1 over b times b plus 1 over a is going to be equal to q. Nice. And now let's go ahead and expand this one, this side. So we have a b plus 1 plus another 1 plus 1 over ab is equal to q. Well, we have ab. How can we find ab? We can check this initial equation and we see that ab is equal to 2. So plugging that back in, we have 2 plus 1 plus 1 plus 1/2 is equal to q. So q would be equal to 9 over 2. Any questions about that? Okay. Let's move on to our last quadratic equation. That actually doesn't look very much like a quadratic. We have this thing. So before anything, let's go. Oh, actually, I'll just give you guys a few minutes to work on this one. Let's discuss this one. So this one's a bit different in that it's asking for the sum of the reciprocals instead of like the sum or the product or something that we're a bit more familiar with. But first, let's go ahead and make this into a more like from a more familiar form. And to do that, let's just multiply both sides by x because this thing is ugly. So by multiplying both sides by x, we get this. And now let's go ahead and call the two roots of this equation R1 and R2. And it's not immediately obvious how to find the sum of the reciprocals because that's definitely not something that's covered. But observe that when you take these two and then combine and then create like a common denominator, you actually get that. Surprise, surprise! It is one thing that we get from Vieta's over the other thing that we get from Vieta's, and those two are both pretty easy to find. So R1 plus R2 is going to be negative 1 over 2003 over 2004, which is negative 2004 over 3. And then R1 times R2 is just going to be that, except positive. So now that we can put those in there, we get negative 1 as our answer. Hope that made sense for everyone. Feel free to ask questions in Q&A as per usual. So now let's go ahead and talk about cubics. And first I'll cover cubics and then I'll go into the beyond example. So like, by beyond I mean polynomials of higher degree. So let's talk about cubics first. So here's a nice cubic, and the tricky thing with cubics is that there's no really easy formula that you can use to solve for the roots of this. There does exist a cubic formula, by the way, but you are free to Google it and attempt to memorize it. I know I have never memorized it, and I have absolutely no desire to. It is absolutely disgusting. But yeah, so in a situation where you see a cubic and you can't easily find roots of it, it's definitely helpful to want to look for information in the form of Vieta's. So Vieta's formulas for cubics states that there are three roots: R1, R2, R3, and it states that the sum of the roots is negative b over a, as you would expect. But instead of the product being c over a, it's actually the sum of each group of two. So it looks like this is equal to c over a. And now, what about d? Well, d is actually going to be, it's going to be negative d over a. Keep in mind that we're going to be alternating. Like this is going to be negative, this is going to be positive, and this is going to be negative. And I'll show you why in a moment. But this is actually going to be the product. And I think you might start to notice a bit of a pattern, and I will go into more detail about that in the beyond section. But let's go ahead and talk about how to prove this. And to do that, I'm just going to pull up the same example, like the same process as before with this. We set that equal to ax cubed plus bx squared plus cx plus d. Now let's go ahead and expand all this. And just to save you some arithmetic, I'm going to just write it all out. That's a pretty bad R. All right, nice. So now that we can go ahead and distributive property it and Just to assign, I won't write that all out again, but I'll just show you that B is going to be negative A times R1 plus R2 plus R3, which then becomes this, which we're much more familiar with. Then the sum of like the two pairs is going to be C over A, and R1, R2, R3 is going to be negative D over A. So yeah, that's the proof for the cubic example. And I'm going to, and now let's talk about, I'll change pen color just to show the beyond part. So, so now let's stop talking about like cubics, quadratics, quartics, and we'll talk about just like the general example of K. So we'll have AK x to the power of K plus AK minus 1, x to the K minus 1, plus all the way to A0 is equal to 0. So now we have this K polynomial, and we want to know what Vieta's discusses. So I won't show a proof for this, but you can actually try that in your free time. Let's call the roots of this R1, R2, RK. By the way, the fundamental theorem of algebra, I forgot to cover that earlier, but the fundamental theorem of algebra states that for a polynomial that looks like this, it will have K roots that may or may not be real, actually. Could be real, could be complex. I won't talk too much about the complex example here, but you know for sure that there are going to be K roots. Some of these roots might be the same as each other, some of them might not be real, but yeah, that's the fun. So we know that we have K roots for sure. So we know that the sum of these is going to be negative AK minus 1 over A sub K. And the two pairs of them well, actually, it'll be like every two pair. So it'll be like R sub I, R sub J for any I, J pairs that are in 1 through K, dot, 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 is going to be positive A K minus 2 K. And then the next one is going to be R1, R2, R3, and so on. So the final one is going to be R1, R2, R3, blah, 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 RK is going to be, all right, A0 over AK, and then that's going to be multiplied by negative 1 to the power of K. So if K is an even number, then the product will be like positive A0 over AK, and if it's negative, and if K is odd, then this will be a negative. So yeah, that's the general form of any Vieta's. So this might be a bit complex, but it's fairly symmetric, should we say. But yeah, now let's talk about how we can apply that in a couple of problems. So let's do this one. And I'll probably move this one down a bit because it is kind of getting in the way. There. Suppose P, Q, and R are the roots of polynomial. I'll change to green. I'll give you guys a couple minutes to think about this. Oh yeah, and I'll keep Vieta's formulas up there if you want to look back at them. let's go ahead and try this one out. So this is another one where we can go ahead and expand this out before anything. This one is a bit more tricky, so let's just walk through how to just how to like expand it. So I'll do these two first to get PQ plus P plus Q plus 1 times R plus 1. That'll be PQR plus PR plus QR plus PR, PQ plus P plus Q plus R, and then plus an extra 1 at the end. Don't forget the 1. So all of these should look pretty familiar. So PQR is going to be the roots of these multiplied, which will be negative 4, which is positive 4. So PQR is going to be positive 4. PQ plus QR plus PR is going to be 3. And P plus Q plus R is 2. So we can just put all of these back in here. So it's 4 plus 3 plus 2, and then plus an extra 1 at the end. So that's going to be 10. Nice. Notice that you can't actually find the roots of this like manually, or at least I don't, like off the top of my head, I can't think of any like integer or even rational number roots. So hopefully there aren't any questions about that. Let's move on to the next one. This one's actually a bit more tricky, so I'll give you maybe a bit more time. Oh, and I'll keep Vietta's laws back up. Hold on a sec. Just gonna grab all this. No, undo. Got it. Paste. So I'll just keep these like right there. Right. All right, let's go ahead and do this one. So first of all, there's not like a very clear way to begin with this. So let's go ahead and just like list out all of the stuff that we know. So I'll erase those and I'll go back to normal. Great. So we know that R1 plus R2 plus R3 is equal to 2. R1, R2 plus R2, R3 plus R1, R3 is going to be negative 11. And then R1, R2, R3 is going to be negative A, whatever that is. Then we also have R1 plus 2R1 plus, oops, plus 2R2 plus 3R3 is equal to 0. I'm going to go ahead and move this one down because it's starting to get in my way. There, stay down. Okay. So there's no really easy way to start with this one besides let's just try and narrow things down a bit. So let's go ahead and subtract this equation from that one. So we have R2 plus 2R3 is equal to negative 2. Then R2 is equal to 2 is equal to negative 2 minus 2R3. All right, so let's just start from there. And let's go ahead and put this one back into this equation right here. So we have R1 minus R2 minus 2R3 plus R3 is equal to 2. Then we have R1. So let's go ahead and simplify that down to get R1 is equal to R3 plus 4. So now we have an expression in term for R1 in terms of R3 and R2 in terms of R3. So let's go ahead and use the equation that we haven't used yet, and that'll be this third one. So we have, this is going to be a pretty big algebra bash, but yep. Times 3 is equal to -11. So let's just multiply everything out. Be very, very careful with this step. So I'm going to hopefully not make any terribly major mistakes. If I do, then just yell at me. Wait, no. Because it's starting confusing. All right, there's that. Now let's go ahead and just combine like terms. So we have -R3 squared. Then there's that to get -8R3. -8 is equal to -11. We'll make everything positive. So 8 is equal to 11. 3R3 squared plus 8R3 minus 3 is equal to 0. So this one can be factored. And I'll pause for a moment. I think I'm going a bit quickly, so I'll just show my work and leave it there for like a minute or so. Okay, let's continue. So R3 is going to be 1/3 or -3. Now let's go ahead and just find R2 and R1. So I'll go ahead and pull our formulas for this down here, there, and pull that here. So our R2 value is going to be, we'll start with this, just the negative, we'll just start with the 1/3 case. So R2 in this case is going to be -8/3. Hopefully I did not make a tech mistake with that. And R1 would be 13/3. Now we'll do the -3 case, in which case R2 would be 4 and R1 would be 1. So keep in mind that A is, so now that we know what that is, remember that negative A is going to be the product of the roots. So when we multiply all of these three, just remember to turn it into a negative. So there's already a negative here, so all we need to do is just turn it into positive. So we have 104/27. For that one, that's a pretty ugly fraction, but what can you do? And on this one, these are all integers actually. Make sure you turn that negative into a positive, so it's 12. And those are our two values for A. Yeah. Okay, one more question. We're actually starting to run like a little bit low on time. I'll actually just leave these up there for a bit, but also just like focus on this question. So I'll give you guys we're running a bit low on time, so I'll give you guys like a few minutes to do this one before I explain. But this one's a pretty tricky one, actually. Good luck. All right, let's just go ahead and finish this one. So I have to kind of rush a bit because we're running a bit low, but I'll change to purple just to differentiate. So let's go ahead and let the three roots of G be R1, R2, and R3. G of X. And I'll let R4 is going to be the extra root of f of x. So just to include that. So we know that because all of the roots of g of x are roots of f of x, and then we're also including that R4 term. Let me just go. Okay, so let's go ahead and start with the Vieta's formulas on just the sums. So we have R1 plus R2 plus R3 is going to be negative A, and R1 plus R2 plus R3 plus R4 is also going to be negative 1. So we know that R4, so we can go ahead and plug in negative A right there to get R4 is equal to A minus 1. That's a good place to start. Now let's go ahead and use some more Vieta's formulas on, let's say, let's just finish up g of x. So we'll have R1, R2, R3. It's going to be negative 10. R1, R2 plus R1, R3 plus R2, R3 is going to be 1. Then R1, And then, oh yeah, and then we're going to use it on this term as well to get that. And it's going to be negative because if this might be handy, but just make sure you label everything negative, positive, negative. No, this one's negative, positive, negative, positive, just to prevent any mistakes with regards to signs. So in this case, we'll have it be negative 100. So we can actually just plug this right here in. So, and then from here, we can factor out R4 from all of these terms. And we also know that what this is. It's just 1, so we'll just cross that out. So then R4 is going to be negative 90. Nice. And then from there we'll just put it back there, and then we can find A is equal to negative 89. What you could do from here is actually find B and C, but we'll take the shortcut by using the thing that we found earlier here. So we have f of x, since the question is looking for f of 1, so we're going to have f of 1 is going to be 1 minus r4 times g of 1. But we can definitely find both g of 1 and we know r4, so it's going to be 91 here, and then g of x, if you look back here, if we put in 1, then it'll be 1 plus a plus 1 plus 10, which will be 12 plus a. So it'll be a plus 12. We have a right there, so it will be 91 times negative 77. And then this, hope you don't make a mistake with the multiplication, because I know I probably would. It would be negative 7,007. Very, very negative number. So that was a pretty complicated question that was made to be pretty approachable with Vietas, actually. So any questions about that can be put into Q&A. I'll leave it on the screen so that you guys can just read what I did. Or I could just zoom out that too. By the way, this document, this PDF, this PDF with all of like what I've written here will be posted onto the Flashmath website. So if you don't catch everything now, then I'll have it up there. So let's just conclude. So in conclusion, for quadratics, I'll change my pen color again because I like colors. Quadratic, Vietas. I misspelled quadratic. How did I do that? We have ax squared plus bx plus c, and the two roots of this would be r1 plus r2, have a sum of negative b over a, and r1 times r2 would be c over a. And then we can extend this to cubics. And just keep in mind that the signs do alternate as you go close, like as you go from here to here to here to here. So this is going to be positive, and then this one is going to be negative again. Okay, So that's all for Vietas. I'll just write cubic over there because that's not a quadratic. So that's all for today's Vietas. There's homework there's like a homework sheet on the website. I'll post an answer key like later this week. But now I'll turn it to Andy and his geometry. So thank you guys for listening to me.